So the third function that we're going to talk about in this section is the graph of secant. And so I want you to remember that secant is simply 1 over cosine. And as we think about the graph, we're going to do it basically the same way we have been doing with tangent and cotangent. First of all, think about what's going to happen when cosine is 0. When I divide a number, in this case 1, by 0, it's going to be undefined. With functions, that often means a vertical asymptote. And so wherever cosine is 0, secant will have a vertical asymptote. That happens at a couple spots. Cosine is 0 at pi over 2. It is 0 at 3 pi over 2. And then any multiple of that, I suppose. Let me continue this just a little bit more. Okay, and then I want you to consider what happens when cosine is at a max or a min. So let's just start with a max. At 0, okay, at 0 degrees, 0 radians, whatever, on the unit circle, cosine is 1. Okay, positive 1. So 1 divided by positive 1 is still 1. Cosine of 0 is 1. That makes this whole fraction 1. So secant of 0 also will be 1. I know that I will have a point right here. Okay, at pi, so at pi radians, I've gone 180 degrees now. The x value there is negative 1. So at pi, cosine is negative 1. That means secant is also negative 1. And then at 2 pi, we're back to positive 1, so we'd be somewhere up there. Okay, so we have some points. This one's going to be a little bit, I don't know, I guess a little bit more difficult. So let's just kind of consider what's going to happen here. Notice that at no point do I really have x-intercepts. There's really no way for secant to equal 0. The only way would be if the numerator here was 0, and that can't happen. The numerator is always 1. So I know I go through 1 right here, and I have to hit this vertical asymptote. I need to keep going, so I have to go straight up right here. I'm going to expect it to go straight up in this big middle chunk. Again, no x-intercepts. I know that this point is kind of fixed. So if I just continue to the right, I'm going to run into this vertical asymptote. It's going to go down here, and it probably goes down right there too. And this will be kind of going like that. Again, not the easiest thing to remember or to figure out, but it does kind of work here. Okay, so that's the graph. You're going to see, as I graph it on our notes, you're going to see a lot of what I'm going to call U's. But I want to show you a real quick way to remember what this light blue graph looks like. I'm just going to graph cosine along with it. Okay, let it catch up here. There's cosine. So the way I remember what secant looks like, I remember that cosine has this kind of upside down U in this chunk, which means secant is reflected. Here I see more of a U shape for cosine, so I see an upside down U shape for secant. That's the way that I remember that. I will gladly put this back up on the screen in class and talk about this some more, but that's just a really quick, easy way to remember what secant looks like. Okay, let's get to our notes here. Erase all this stuff. There we go. Okay, again, I'm going to pause this really quick, get a good graph of secant, and then we'll look at our application problem. So if we were to continue the graph that we saw on Sketchpad, you'd see the left side, you see a lot of different, what I'm going to call U shapes. To me, that's the easiest way to remember what secant and then later on cosecant kind of look like. Just the nice, easy connection for them. How do we typically use the function secant? We often don't refer back to this graph. I think we often use cosine as our our way to solve these kind of questions. So consider the question that's to the right of your notes here. And this is no calculator. It says find the value of x between pi and 3 pi over 2 where secant has to equal -2. So first thing, if secant has to equal -2, that means that cosine has to equal its reciprocal, which is -1/2. Okay, and then we go through and we maybe draw a bit of a picture for this. Draw a coordinate plane here. Switch colors. So we are in the angle measures of pi and 3 pi over 2. That is in the third quadrant, somewhere in this area. And I need to create a triangle in here in such a way that cosine would fit this fraction. Remember, cosine is adjacent over hypotenuse. And so I'm going to maybe do something a little bit like, maybe this will be my point right out there. Okay, here's my right triangle. So if this is the angle measure that I'm talking about, if that is my theta, that means adjacent would have to be -1 because the hypotenuse has to be positive. Okay, and then if I think through what I know about my special triangles, and I know that because it's no calculator, it's got to be related to 30 degrees, 45 degrees, or 60 degrees. The only thing that really makes sense with these numbers is to have this be a length of √3. In this case, -√3, because we're in that third quadrant. Y values have to be negative there. So what kind of angle measure would make this work? Theta, in this case, would have to be, let's see, well, we're in radian mode, so I want you to remember that. We are in radian mode. Theta, or x, I guess I should have called it, would have to be 60 degrees or pi over 3 radians. Okay, in this kind of triangle, square root of 3 and 30 degrees kind of go next to each other. This would be 30 right here. That means this is 60 or pi over 3. But I want to think through measuring in standard position, so I'm going to start along the x-axis and measure this way. This is pi radians, or 3 pi over 3 radians, right? 3 pi over 3 reduces to pi. So 3 pi over 3 radians plus another pi over 3 radians gets me 4 pi over 3. And that's really the answer that I want. Now, that is a great way to solve the question. You can also certainly get this answer by using our hand trick, and I am more than willing to explain that process in class. Just be willing to ask a question. So I'll stop right there, and we will see you in class.